Hello, hello. Thank you for joining. Hello and welcome, and thank you for joining us today. Hey, Ruslan.
Hi.
Uh, so, my name is Harry from attendees who have been in other of our webinars. I am part of the team of Additive Plus. We regularly host technical webinars like this one, covering different additive manufacturing topics about technology, materials, and it's great that we are having some people that have joined other webinars again joining this one. So, to start, let's start again with a quick presentation about what is our company. Our company is Additive Plus. We represent 3D Ceram in the US. We are located in the West Coast and also have warehouses around the USA. So we have, in general, more than 15 years of experience working with Additive World. And our approach is basically focused on providing a full production system, not only the standalone machine, but also to provide the process, also to provide the engineering. So after this, we also have under our scope of approach to provide stability, repeatability, and scalability for the production of basically any material or with any technology of additive manufacturing. And we are very well known about being one-stop engineering solutions provider. Since, for example, you can come to us in case you need, for example, a solution to work with some special materials, some advanced technical material. You can find the machine, the support, and also the engineering support on our site. Our experience has made us an OEM supplier, and this has also gave us the ability to develop our own machines. For example, in Additive Plus, we have developed the brand AO Metal, which is a line of very powerful metal systems. We were able to develop this system in the United States to supply national laboratories, to supply critical applications, because it allows to work with a very, let's say, difficult materials with open parameters, and that has a local support, and also that is very powerful and affordable. So a quick example of what we do: we have a turnkey additive manufacturing ecosystem where our additive manufacturing equipment, our metal atomization ecosystem, also our team for design and manufacturing of parts and OEM capabilities has made us a reference for additive manufacturing. So we would like to say that we are open to work in any projects that you have. And if you want to schedule a one-on-one session with anyone from our team, we are very happy to do it. Our role in ceramic additive manufacturing is being a partner of a 3D Ceram for many years. We provide a 3D printing service in the USA, also for some leading companies in the market in advanced ceramic, technical ceramics. And our vision to fulfill the needs of our customers is understanding all the ceramic process and the materials to fit the customer applications. We give access to choose the right technology, because when we work with ceramics, we have different options to go. We are happy to run testing and validations in any material you want to work. And of course, we support all the implementation of the technology until you have the production setup or the R&D setup that you envision. So this said, I would like to again introduce my colleague Ruslan. He represents 3D ceramic in this session, and he will be sharing more about ceramics technology in additive manufacturing.
Thank you very much, Harry. Thank you all to join us at this webinar. My presentation today is ceramics 3D printing for mission critical applications. So you understand it will speak about military, about space, about other applications in relation with this critical use of advanced ceramics. Just a couple of words about me, about our company. So my background is ceramics for more than 30 years now, additively manufactured ceramics for 8 years. And if we speak about the company started more than 20 years ago, and we started from the printing. We start to develop these different applications, start from biomedical, but over the years we came to another business model. And today we are part of big Japanese group Sinto Kojur, the industrial strategy of which is to develop additive manufacturing of ceramics and manufacturing of advanced ceramics in general. So some of you maybe know that in 2025, we consolidated and created a group called Sinto Advanced Ceramics with big players in Europe like Bosch Advanced Ceramics being part of this group. So that the ambition and is to become an important player in ceramic, advanced ceramic part manufacturing. And additive manufacturing is one of these aspects that we represent. We are based in France. We have our own production facility when we assemble our printers, and our position is being process provider. It means that we manufacture our equipment, we develop our own software to facilitate this 3D ceramics 3D printing with integration of AI. For last 3 years, we do develop our own formulations, ceramic slurries to print with. And of course, we run the old kind of dedicated services going from the training of our customers, installation of the machinery, but also development of some applications and parts before they buy the equipment or before they understand how to produce this or that part. So just the overview of different technologies that you know, but speaking about ceramic additive manufacturing, which is a little bit younger brother of metal or polymers additive manufacturing. So this is the overview of different technologies existing today, DLP, SLA, sheet lamination, binder jetting, etc., etc. Our technology is called stereolithography. We speak about wet polymerization. To print, we use ceramic slurry composed from the ceramic powder, which is our basic material, and photosensitive binder, organic binder. So this mix has the consistency of yogurt to drink, for just to imagine. And we dispatch this mix layer by layer by the recorder on the build plate, and we cure or we polymerize using the UV laser of 405 nanometers wavelengths. So when the layer is polymerized, we put another layer. So we build this part layer by layer. So this is for general explanation of how it works. Our 3D printers range is very simple. It is by size. So the smallest printer is about 100 by 100 by 150 millimeter build plate, and the biggest one is 600 by 600 by 300 millimeter, which is actually the biggest machine on the market to make big size parts, for big size dense ceramic parts. Before speaking about the application general approach, we have when we discuss with our customers or where we have some requests, it's about qualification of material first and the qualification of the application of the process to do this or that part. When we try to understand what are the expected properties of the part the customer wants to have, and we try to advise, recommend with extent of our knowledge, of course, because we are not experts in every field, application field, and for this, the discussion with the customer is very important. But we try to bring our experience of our expertise of shaping, because 3D printing is just the shaping of ceramic parts, to understand what would be the most adapted material for this or that application. It can be because of the mechanical properties, because of the thermal properties, electrical or dielectrical properties, etc., etc. Because every part will work in some specific environment that we try to understand. What will be the temperature? What will be the pressure? What will be there thermal shocks or not? Of course, generally, we are speaking ceramic parts, they are operating in harsh environment, and often advanced ceramics is about this. But every environment is different, and sometimes ceramic materials we recommend or we will print with are also different depending on these conditions. So we also try to understand why customer is exploring this technology. I mean, it's just a prototype to do some validation of R&D studies, or it is just small series of production, or there is an intention to install the machine. We cover all this, so we can respond to all these kind of requests, but this will help us to understand how we treat the request, how we go, should we manufacture proof of concept parts, should we develop or consider economic effects, for example, for the customers who intend to install this machine in-house, etc. So the co-development with the customers, I call it co-development or co-engineering, is very important because we try to understand what you guys need from this technology, what you expect from this technology, because as you know, maybe from other materials, additive manufacturing is not always the right solution. It's just not the miracle technology. It can be very beneficial for some study cases, but for others, it will be just repeating the process that you master for decades, and it's not cost effective. Advanced ceramics are, and now when we speak, I am in this field for 8 years, as I said. So when I compared the request from the beginning, I mean, 8 years ago, people was just wondering why ceramics, how we use them, etc. Now we see more and more companies, more and more engineers interested in new advanced materials, and they try to understand what benefit will be provided by this ceramic material. So they compare different properties of ceramics comparing to metals or comparing to other materials. And here is just the example what can be compared. Modulus of Young, density, but also thermal properties, thermal conductivity, or other properties we maybe speak less, like transparency, or it can be transparency to visible light, it can be transparency for electromagnetical transparency, etc. So all these properties are needed for certain niche applications, and some of them I will just share with you today. Before, just some words about the materials which are available in our standard portfolio. So ceramics are, there are many ceramics. I mean, clay is ceramic, porcelain is ceramic, but we are speaking advanced ceramics, I mean, pure ceramic materials, which we divided in two big families, oxides, non-oxides. So among the oxides, we have common materials that you might know, like alumina, zirconia, but also ATZ, HAP, and others. We have transparent or translucent alumina in our portfolio. And for the non-oxides, we have two main materials, which are aluminum nitride, silicon nitride, and which become very, very, interesting for some of this application. Just to say a word, here you see the note that we do not provide sintering kilns for non-oxides. Usually we can provide, as I said, we are process provider. We provide the full range of equipment necessary to print parts, but also to post-treat the parts, because after the printing, you need to have the thermal treatment, you need to debind the part to remove the organics, and then you need to sinter the part to densify the ceramic part and to give to it final properties. For oxides is easy. We can supply the full range of equipment. We are working in collaboration with different vendors, like Carbylate Geo that Additive Plus is distributing as well. But for the non-oxides, it's another story. And when we speak about aluminum nitride or silicon nitride, these kilns are very specific, very costable, very expensive. So we can guide it to some of the vendors we know, but usually this kind of equipment is out of the range of our supplies, of our scope of supplies. Three different options we have for the materials. This is also the question sometimes our customers ask. So they are not obliged to buy our materials. Our machines, our printers work either with our materials, of course, but they are not locked to our materials. So we can develop new materials with you on demand for extra cost. This is possible, and we have big experience for some niche materials or proprietary materials. But the machine is also open parameters, so you can create your own formulations. If you have the access to some specific powder, you don't want to disclose its composition, you can work on this development in-house if you have our equipment. And our software, it's a separate discussion, and if somebody is interested, we can do some individual meetings, team meetings, but we have the software solution which help you to do this. Now, straightforward to the application. So as I said, mission critical means often defense, airspace. So I will stop today by these two main applications, which are not really, you cannot say that this or that ceramic part or this or that ceramic materials is only used for defense, or it's only used for airspace applications, because often these applications are just crossed, and you might have some airspace part, but for defense or civil, and the same will be for healthcare, and the same will be for electronics, for semiconductors, etc. So here I will try to just to give you some experience we had. I will speak about the parts which are used or which are under development. So this is not just theoretical conclusions, it's something that we experienced in the past and that we print or printed or our customers print. Again, as I said, the key word is the material. So first application I would like to share, it's 3D printed ceramic radams for, you can understand the use. So it's defense, military, for different kind of applications. I mean, for different kind of frequencies. And here, again, we are speaking about the material properties. If you take the material like alumina with the permittivity of one value, like 8, and you take silicon nitride, who will have different permittivity, you understand that the use of these two materials will be different. It's also combined with the mechanical strength or mechanical resistance of the material, because the best one, which is transparent to electromagnetic rays, is silica, for example, but its mechanical strength is very low. So we are developing with our customers, and this, unfortunately, I cannot really disclose, some materials which will be combination or deviation from the ceramic standard materials we have. So this is that what we do, and you can see the example of some radams we could print to understand that 3D printing combined with the material science can give you good results in terms of the permittivity. So you can see this lattice structure radom in aluminum that we printed. You can imagine that, I mean, the 3D printed structure gives some benefit, some advantage in terms of the permittivity for the material, which is not maybe good, basically, from this point of view. Silicon nitride radom is also another example. So here, the conclusion is that we play with the material, we work on the material properties together, the density, the property, the purity of the material, but we can also combine this work on the material with the work on 3D printed structure, lattice structure, gyroid structure, sometimes tiling of internal structure of the radomes to make selective frequency radomes. So all this is the benefit and the advantage of 3D printing, because any other technology, no other technology can do the part which is in the middle of the picture. It's impossible. We can print also transparent, when I say transparent, transparent to the visible light materials. So here are examples of alumina, which is translucent or transparent alumina. So it's not really standard alumina, it's a little bit different powder, but with some post-process like HIP, we can get translucent or transparent parts. YAG, it's another example of the transparent ceramic parts. So these materials are not available as a standard, but they can be supplied on request or co-develop it with the customers based on the proprietary or even commercial powders. Another topic which is important for and is studied right now by different institutions is ballistics. So ceramic combined with 3D printing, again, can give good results for the ballistics. Of course, some materials like B4C and are already used, but they are very expensive, and we do not pretend to replace this material everywhere. However, geoid structure, this kind of structure that you can see, just an example, of course, combined with the hardness of zirconia or some zirconia deviated materials, can give good results for some specific ballistic protection units. The topic for which is civil, it's dual use, let's say, it's energy. Energy is important, of course, for civil life. A lot of people is working on solid fuel cells or solid electrolyte cells, but here we are speaking about power to gas or gas to power. For military applications. So imagine the troops on the field in the middle of nowhere without any source of energy, but having some miraculous solution to produce the energy during the day using the sunlight to create some gas like hydrogen, and to use this hydrogen by the same device in the night for to generate the energy without when you don't have the sunlight. So this is dual use. A lot of people is working there, and we have some good materials like zirconia 3 yttria, zirconia 8 yttria with high ionic conductivity. Again, combined with some specific honeycomb or geoid structure, it can give good results for these kind of devices. It's not yet an industrial solution, but the studies are well advanced, and the TRL for some of them are rather high. So we have good experience in this as well. And one of the projects maybe you heard about this. It was with European findings. It's green hydrogen production, solid electrolyte cells, where we collaborate with different entities in Europe, including Institute of Energy in Barcelona in Spain, but also other institutions like DTU or some industrial partners to produce this kind of corrugated shape solid electrolyte cells from zirconia for the purpose of generation of hydrogen. If somebody is interested more in detail by this topic, we can do some presentation, individually, but just to say that here again, what additive manufacturing brings as advantage. You can see this corrugated structure under the main picture, and this corrugated structure versus flat solid electrolyte cells manufactured by tap casting gives more efficiency, not only in terms of the production of hydrogen, but also it provides much better mechanical resistance to the cell, because the biggest issue with the flat cells is reliability and the capability to work under pressure to produce hydrogen. Here we could solve this issue, this challenge, using 3D printing. So it's really about the advantage that additive manufacturing can bring. You cannot do this by tap casting. Not only you can do this corrugated shape by 3D printing, but you can also integrate some features, additional features to your part. Like here we have these gas evacuation holes and other channels. Why just to simplify the metal interconnects within the stack, energy stack. So by the end of the day, your energy or production, hydrogen production stack is just much more compact, 35% of compactness, of size less, and more efficient than traditional stack of the same size. So, of course, the development of this took a couple of years because we had to explore different shapes, different corrugated shapes, let's say, different thickness, different even materials. But the idea is, again, the collaboration, the co-development with the customer, because this process is not just about the printing. We have to think about the debinding, we have to think about the sintering, and ceramics are challenging in general. So you might have the issues to resolve, which are in relation not only with the technology used to process the part, but also with the properties of the material itself. If you, I mean, one of the advantages of this SLA technology is the possibility to scale up. If you remember at the beginning, I showed a different range of different size of printers, and the biggest one was 600 by 600 by 300. This is possible using laser, and this machine we use 4 lasers, and this machine is capable to make big parts. So if you use the small machine to development, you can imagine the process. You can develop something during the R&D stage and scale up to industrial production, either to make bigger parts, it's not always necessary, or to increase the output of your printer. So your printer becomes not only the R&D lab tool, beautiful toy you have in the lab, but also the industrial tool, which is working to make real production. And I don't speak about this example in this presentation, but we could even make the customized printers, which are working 24 hours a day, 7 days per week without any downtime. This is possible. And for those who already operate some printers, know that usually they are standalone machines. You need to clean the printer, you need to prepare the printer for the printing job, so it takes time. Here, this machine avoids all these situations, and you can print without interruption. So this is real industrial machine, and our goal is to integrate these machines industrially, not only to make parts here and there, but also to have continuous production chain. So here you see the example of big parts, just to show it's possible with this technology, different parts for semiconductor industry, but also for space industry. You can see, sorry, I just skipped this one. So this part is really impressive. For those who visited us at Formnext November last year, could see this part in real. So this is the semiconductor part we printed in alumina on the big machine. And just showing this, I can tell you 3 years ago, I know this because I'm sales manager, we were not able to print the parts. So here comes our process provider side aspect. We develop also software solutions, and the software solution now for our printers integrates AI. And this AI not only helps us to optimize the printing job, to optimize the printing time, to optimize the consumption of the slurry, but also makes us capable to produce parts that we were not able to produce before. So this part typically a result of AI integration in our machine. Space industry. Space industry is like military. It was more or less closed before the new space company appeared, and new space company brought new dynamics in this development, and new space companies start to use more advanced materials, start to use this additive manufacturing as the tool of democratization, because new space companies, you know them, we all know, I mean, the big ones, but we have a lot of small, in Europe at least, we have hundreds of small companies specialized in this or that component of the satellite or specific vehicles or specific parts or components. And these companies are very dynamic and really study and turn to additive manufacturing, find a good way to produce parts in very low cost. Again, here we speak about the material. So usually, and this list is not exhaustive, we use zirconia, alumina, but also cordierite, which is dense cordierite. We call it also optical cordierite material, the main property of which is low coefficient of thermal expansion. So you can imagine in space, when you go, temperature goes from minus 150 to 150, the material has to be stable, and the support, for example, has to be stable. So a lot of applications for space industry are based on this property. Two examples here I give. All of them, I mean, both are already used in space, so it's not just the parts we printed for demo, they are real parts. One of these is antenna, S-band antenna for non-satellite from the company Anywaves, European company. We could develop this from scratch in 18 months. So 18 months to do all this research work, to unrisk the production, to bring the part from the scratch, the drawing during the breakfast or the lunch between two engineers, up to the industrial production. These antennas are already flying. Another part is the component, alumina component for Hall effect thruster, company Trust Me, maybe known also in US, very known in Europe. So this company also uses 3D printing for the parts used in space. So different application, but still the same approach, same philosophy. When you need to do small series or customized parts or something quick, you don't need tools for additive manufacturing. You can change the design as you want during the development work. So you can reduce the time to market very, very dramatically. And this what happened with the collaboration with this company. But space industry is also about the big parts. And I really emphasize this point because SLA technology is able to do big parts, and we have more and more players interested in big parts printed by additive manufacturing. Why? Because most of these parts are consumables. Most of these parts are very, very costable. And with all the issues we know now for geopolitical point of view, supply chain, COVID, etc. So if you want to have some sovereignty, some independence from your suppliers, which are always overseas or very often, you might have interest to install this technology in-house and to print these parts for yourself. And 3D printing, ceramics 3D printing gives this possibility. So here just example of some telescope mirror from silicon nitride, some specific supports also for space industry, but it can be for any other industry, of course, for automotive, for airspace, for defense, etc. This is the case, study case from Thales Alenia Space, so also airspace application. The silicon nitride support, demo support, because we can disclose the real part, but you can see the particularity of this part, just some specific shape, which can be modified by software very, very quickly for the production. You can imagine if you need the tooling to make this kind of part by injection molding or pressing. It takes months. Not the case with 3D printing. Finally, thermal protection system. I think a lot of people know that ceramics are high temperature resistant. Yes. And some of them are thermal shock resistant. So here is an example of silicon carbide part we printed for, I think it was for NASA. It's a demo part. A couple of years ago, it was printed using another technology I will speak about after, but the idea is here. You see the lattice structure, you see the part. We can do it in very, very short period of time, and we can develop, we can modify the design, we can play with it, test the part, and go back to modify the structure of the part as we want. Of course, space applications, again, the list is not exhaustive, it's just about what we know and what we can speak about. But here it's an example of other parts which we print in the past for different players, either during the pre-flight test or for R&D studies. To summarize, I mean, SLA technology is one of the most accurate and most accurate in terms of 10-dimensional deviation technology. This was studied by some independent bodies. We are let's say, in second place after the subtractive technology. But we also integrated so-called multi-additive technology, the printer you can see on the screen right now. Why we did this? We did this for several reasons. One of the reasons is because SLA, as I said, is using UV laser, and UV laser is used to polymerize the organics in the slurry. Unfortunately, not all the ceramics are sensitive, are reactive to this UV light. Some of them, especially carbides family, is not really, we call it also dark ceramics. It's not really, we cannot process or in very, very restricted conditions to print these parts using SLA technology or wet polymerization in general. So we could develop the machine, which is a versatile tool, which can host different extrusion-based technology combined with CNC green machining tool. And this machine, we call it MAT, multi-additive technology. It's more affordable. It's not for industrial manufacturing because you cannot print several parts in the same time. It is mostly for R&D, academia, and functional prototyping. But the advantage of this machine that you can combine it. First, it was developed really for ceramic materials, not for polymers embedded with ceramics. So we can print really dense parts with this. And we can try or use different heads, different technologies. FFF, fused filament fabrication. We can use extrusion, direct ink writing. We can use direct pellets extrusion. And all of this can be combined with machining. The advantage of this machine, comparing to SLA, first, this machine is multi-material. We can do ceramics, but we can also print metals. We can print copper, we can print titanium, we can print stainless steel. The machine is equipped with all necessary features, the chamber heating, the plate heating, the filtration tool. And it's not sensitive to optical properties, as I said. I mean, in theory, you can use any ceramic powder to put it into thermoplastic matrix and to print with the filament, for example, with the pellets. Of course, in theory, because we just didn't study all of these ceramics, it's impossible. But we have pretty good experience with some of them. And this machine, it's a really nice tool to go for development. And last and not least, it's a low-cost investment. The capital investment for this machine is much lower than for the SLA printer. So that's why this can be a good entrance tool to start with ceramics 3D printing. Here, just the list, not exhaustive list of the materials we can process with this machine. So you see alumina, you see zirconia, but you see also silicon carbide. And this is really space-grade silicon carbide with a density over 97%. It's pure silicon carbide, not silica impregnated silicon carbide, so it gives some different properties. We can print stainless steel, as I said, different grades, grade 5 titanium, copper, and also even polymers up to the temperature of the maximum nozzle temperature on this machine is 250 degrees. So you cannot print some high temperature polymers, but you can print the most common ones. The different heads are proposed for this machine. So one of these feature is direct ink extrusion writing head or paste extrusion head. For this, we can propose the simple one, but also the most complex one with the two components, possibility of two components mixing. The mixer is inside of the head. Of course, it's not for the production, as I said. So the volume of the hopper we have for this machine is very small. It's about 55 to 60 milliliters. But it gives you the possibility to start to develop some materials and to see how they behave during the printing. I hope I can see. No, you can see just the picture. I'm sorry, but yeah, okay. You can see this. This is the example of the printing using this direct ink writing head. It's different technology. It's not as accurate as SLA, but it gives you the possibility to develop your own material because we don't supply the materials for this head. And usually it's a lot of, a lot of people is working with this technology for some specific very niche applications. We have another head which is called direct pellet extrusion. So here the idea is simple. You print the parts very fast using the pellets, which are also used for ceramic injection molding. So traditional ceramic injection molding, you take the pellets, you put in the machine, and you can print. What is the advantage comparing to fused filament fabrication, for example? For FFF, for those who know the FFF or FDM technology, you have two-step debinding. You need to remove organics chemically, and then you have some thermal debinding for organics. Here, for most of the pellets, except maybe specific ones like silicon carbide, the organics are water soluble. So you do not need this specific chemical step when you put the part in the acetone, heated acetone bath. You just do it with the drying. So the part cost and the speed of the time of the printing is very, very high. And finally, as I said, the machine is all these heads are combined with green machining. So you over extrude your part and you can just without moving the part from the build plate, still fixed after the printing, you just remove the upper layer of the part to enhance the density of the part, the overall density, but also to enhance the roughness of the part. So here, just the example. I don't know if it works for the video, but we can do the machining, the green machining once the part is printed, but we can also do the printing. For example, you print 5 layers and you machine 5 layers, you reprint 5 layers, you remachine 5 layers. So it works in both ways. Uh, Here's the example of this, possibility that green machining gives. It's not only in terms of the roughness, but also in terms of the accuracy, dimensional accuracy. Because speaking about ceramics, as I said, ceramics are challenging. You have the shrinkage to deal with. And this shrinkage, sometimes if you need to meet very tight tolerances, you need to machine the part. So here you can see the example on the video when you print the part and during the printing you remachine. So this is, as I said, a development tool. It's not production tool, but it's a very good machine to make R&D and to make functional prototypes very cheap and very quickly. The list of materials I just present is not limited, so we could also work with some conductive ceramics. We could develop some materials like regolith, for which also has applications for space industry, for example. So any interior, as I said, any ceramic powder, you can put it in into thermoplastic matrix and use other like pellets or produce the paste to extrude or produce the filament. So here's, I'm sorry for the time. I think it was, we still have time for the questions. So you are welcome, guys. If you have some questions, technical or commercial, me and Additive Plus team are available to answer.
Okay, so maybe I can ask you something by audio.
Yes, of course. You're
Hi.
welcome.
So, this is Tobias from Germany.
Yeah.
First of all, thank you very much for your presentation, and I think it's impressive what has been achieved during the last years for ceramic 3D printing, especially for silicon nitride and aluminum nitride. So, my questions are about the shrinkage of printed parts for silicon nitride and aluminum nitride. You touched it a little bit, and for sure, main target is to have it without any machining. Is that reproducible, that you can already print these materials without machining directly to the shape you want to have?
Yes, the parts I showed, from silicon nitride, just try to find this slide. Yeah, here. these parts are as printed. So when you see the first, the roughness of the surface, you are impressed. I mean, for those who do not know really additive manufacturing, and they use it to see these FFF manufactured parts, or you see when you see the layers, etc., you don't really see any of this on SLA printed part. Now about the shrinkage, about dimensional deviations, we are using the slurries, and this is your question gives me the opportunity to speak about it a little bit in detail. This technology gives the possibility to use high loaded slurries. It means that we have big volume of powder versus organics in our slurries, and bigger is this volume, less is the shrinkage. Usually our shrinkage for different materials, and I don't want to lie now because I don't have the right figures, but we are, I think for alumina, we are at the level of between 17 and 19% of shrinkage. And for silicon nitride, maybe it would be over 20%, but between 20 23%. So why I'm saying this? I mean, it seems to be big, but when the shrinkage is something repeatable and we control this really, we can apply the scanning factor. With some challenges, however, for this technology, when you use the machining, your part is fixed. You have 0 point to fix the part, so you can calculate, and you can, using more or less accurate tool, you can do your drilling, you can machine the part in very accurate way. We don't have this in 3D printing. We have non-linear shrinkage. X, Y, and Z have slightly different shrinkage, but that's why we integrate all these software tools and AI to limit the impact of this technology on the final dimensional deviations. To summarize, we are in the medium range of ISO 2768. So we are speaking the accuracy of, let's say, 50-ish, 80-ish microns for the parts. But it will depend on the size. On the big size part like this, of course, we will be more like 200 microns precision. Sometimes for some parts with very, very tight tolerances, we need to produce the part and then to machine it. Of course, it's difficult for silicon nitride because it's very, very hot material. But, well, that's why I'm speaking. I'm saying that this technology is not adapted for every application. But as you said, we did a big progress specifically for the non-oxides. And you are welcome to send us requests for some specific parts. We will review them and we will tell you what we are capable to do or not. But we are in the medium range of dimensional deviations.
Okay, thank you. Maybe you allow me a second question. Do you have an example for aluminum nitride printed?
So, sorry, can you repeat?
Do you have an example of aluminum nitride printed?
Not in the presentation, but it's a good question. I didn't see in my presentation aluminum nitride part. But no, not here. I'm sorry for that. But aluminum nitride is used mostly for electronics, so it's not big parts. We could do big part. Maybe my colleague Eric, you can help me with this. You know maybe better what we printed from aluminum nitride, but this material is used mostly for its thermal conductivity property. So a lot of application in semiconductor industry and electronics. Right now, unfortunately, I don't have the part to show, but we can send you some pictures, or we can share some pictures, I mean, from aluminum nitride parts, for sure. We have good experience with this now.
That would be very interesting and appreciated. Thank you.
You are welcome, Tobias.
All right. We have a couple more questions. So one more question we have in the chat. How is the flatness of the large flat parts?
This is the question from ceramic manufacturer. Yeah, it's a challenge. It's a challenge, and you need to, I mean, as I said, we try to consider this process. I mean, not only the printing part, but also the thermal process. And sometimes we can print the part, we can debind it, and during the sintering we have distortion. And of course, big size part with the low thickness, you have more risk to have this kind of distortion. We use the skills, internal skills of the group. As I said, from the beginning, we are part of big groups in Sintocogio, and Sintocogio has company Viserax, which is, a ceramic company from Japan. So we use the skills from this company. We use the skills of our colleagues from Bosch Advanced Ceramics to understand and to deal with these issues. But yes, we might have these issues like any ceramic part of the same size produced by any other technology. So 3D printing here is just the shaping, but you still have to deal with the common challenges of ceramic parts, and we try to fix this using the internal our group internal skills, because we are not experts in everything.
Great, thank you very much, Ruslan. Uh, I have another question. How important are fatigue properties for these applications, like meaning the mission critical applications?
Again, this the keyword is a property we are looking for. We try to understand what will be the main property the customer is looking for. For some, speaking about radomes, the dialectical strengths will be very important, or permittivity will be very important, but also mechanical strengths. So often it's a combination of two main properties we are looking for. Speaking about aluminum nitride, our customers speak about the thermal conductivity value and about mechanical strength value. So these two values, but not, they are not the only values they target, but these are two main properties we are speaking about. And of course, we can share, and this is also, Harry, I think you can send the literature with the data sheet of our materials to make people understand what we are doing and what our materials are.
All right. Yeah. I sent in the chat the point of contacts where you can request, for example, the recording of this presentation, or you can ask for the material catalogs and data sheets. We would be very happy to share them with you. Also, if you want to arrange a one-on-one session, just let me know, and I will be very happy to send you an invite. So, do you have any more questions?
I see in the chat we have some question from Gerard Ortelt. I'm sorry if I misspell your name. How important are fatigue properties for these applications? For sure, they're important, and we cannot. This is the kind of work our customers do. The testing. Sometimes the testing takes time because fatigue tests take time. We don't always have the feedback for obvious reason of secrecy, and we are speaking defense and space, so we are not always aware about the results. But from what we know, that the properties of additively manufacturing ceramics and traditionally manufacturing ceramics are rather similar. So that's the only thing I can say right now. After really each test, some tests are really specific, and we do not, in our facility, except for some, for the properties which are defined in our data sheets, we cannot do too much test because each application requires specific properties again and specific testing. The question from Dominique Vita: sintering solves Z-axis strength issues. I'm not sure to understand. We have the Z-axis strength issues. Eric, my colleague Eric Louradou, which is also present in this webinar, maybe you can help me with this, Eric, if you...
Yeah, I just had an answer. So
okay.
We reach 700 MPa, for instance, for silicon nitride when we are on XY and almost 600 MP in the Z-axis when we print vertical or horizontal bar, for instance.
Is it the answer is okay, Dominique? Okay. You are welcome if you have some other questions by chat or by audio. So. Anyway, if you have any questions or any more, requests, so we are available. Harry sent the contact data, so you can contact me as well. I just show the last page of my presentation with my email address as well. And I will be happy to see you guys, for some individual meetings if necessary, if you want to explore a little bit more this technology. So as I said, we try to understand why our customers are interested to explore this technology. We do not just propose the machine and okay, we give the quote and that's all. We try to understand, we try to help you to explore this technology. We tell you if we consider it's not relevant, or it will be too expensive. So really, we try to understand, to listen to you, and to accompany you in this development. So you are welcome. If you have any questions, please contact me. You see my email, my phone. I'm based in France. And of course, our technical team, Eric Louradou, is our material science and application engineer, is present here. So we will be really happy to answer you.
Okay, thank you very much again. So I hope to see all of you in a new webinar. We will be informing through our social media what are our plans. Also, feel free to suggest if there's any topic of your interest, and we will, of course, consider this for a future event. Thank you very much once again, and see you next time.